show the nebula is the color palette that will most or best accentuate the details in the nebula. The Hubble does that too. The Hubble has a specific palette. I use the Hubble palette when I process some of the photos sometimes here. And there are different colors and for different types of emission coming from different types of elements in these gas clouds. Okay. However, the Shamrock Nebula is known as Sharpless 205. It's actually SH2-205 for those that want to know. And it's in Camelopardalis, the giraffe. And right now, when the sun sets, I think it's kind of in the western part of the sky, more to, kind of midway toward the northern side of the sky, because it's sort of a more northern constellation. But it's really interesting to look at the Shamrock Nebula in this false color. But it really is a ionized hydrogen region like many other stellar nurseries and diffuse nebula that we see. So that means it's red, and we look at it in the visible light the way it should be. Anyway,
may I say, if you see,
Daryl probably has something to say there.
I'm sorry. Yeah. If you see the image there, if you follow that link that Amanda put up, a Shamrock Nebula, the image looks very much like a Spitzer Space Telescope image, just the coloration. If I had to guess, that's what it is. You mentioned it was infrared.
Yeah.
And Spitzer is an infrared observatory.
It is, but you know what? The Spitzer mirror is less than 3 feet in diameter.
Uh-huh.
And the James Webb Telescope mirror will be 21 feet in diameter. Do you have any idea? You do, Daryl. But for all of you listening, that means we're going to get such higher resolution on everything we look at when we have the James Webb Telescope up there. And we're getting very excited. And I know when I talked to Keith Akes from P&K Science, Keith and I were talking the other night, and both of us are really hyped on the James Webb Telescope, and we're going to do a special on this, the James Webb. And it's really going to be a groundbreaking system. It's going to change the way we view the universe. It'll be able to see the atmospheres of planets. It'll actually be able to see if there's methane and carbon dioxide in an atmosphere. Sadly, it won't be able to look for oxygen because oxygen's telltale signature occurs in the visible light range, and the James Webb is an infrared telescope. All right. However, looking for methane and carbon dioxide and seeing them together at certain quantities, it will be very hard to say this wasn't created by something living. It'll be very hard to say that. And it means that oxygen will follow, potentially. So that's, and I say potentially because you just don't know for sure, right? So that's a really interesting finding there. When we get the James Webb up, it'll be just beautiful, And Daryl, you must have something that you want to say here.
Yeah, well, just in defense of the Spitzer Observatory, it has done some beautiful work.
Yes.
And if you go to YouTube and search for floating along the Milky Way, it will show you an absolute knockout of a video from imagery taken by the Spitzer. Highly recommend it. One of my all-time favorite videos.
Yeah. I love the Spitzer. And for what it was at the time, the Spitzer gave us the most beautiful imagery ever. But now, Daryl, I want you to just imagine the same video done by the James Webb. And now imagine it done in high resolution, and imagine it done in 4K, the highest resolution video we can do right now, practically. And then imagine it done in 3D.
Okay. Oh, I agree. Absolutely.
And then make it a 3D journey through the stars. Yes. And that's something we've been working on, not us personally, but I've been working with Douglas Trumbull up at his studio. And Doug and I have been doing stuff like this for like 6 years. We got a test movie out using the MAGI process, MAGI, which actually does that. It's incredible, And, if you're ever out here, Daryl and Amanda, you're going to have to make sure that you get up there to see the movie that we did. It's amazing. And for all the folks out there, if it becomes downsampled so that we can actually show it, then I'll make sure that you guys know where to look for it and find it too. All right. So I just want to move forward a little bit because I know that we're we're just eating up precious moments here. But I do want to say, in defense, actually, in addition to Daryl's defense of the Spitzer and my discussion of the James Webb, they're going to help us with the studies of exoplanets. They have the Spitzer has, James Webb will. Now, as of January of 2019, we have nearly 4,000 planets confirmed. Okay, and that number is 3,926 that have been confirmed, and that's from all the various sources. Okay, now it takes a while to confirm whether we have a planet around the star. We can see a transit where the light of the star is dimmed slightly because a planet is passing between us and the star. Right? But we have to wait. We have to wait for that star to rotate around because stars are all rotating, and we can get the rotation rates of the stars. And when we do, we have to wait for the star to make rotation so we can see if that dimming of the light was due to a magnetic storm on the surface of the star. And if it's not there, then we know that what we saw was a transient stellar magnetic storm. In other words, like sunspots on our sun, because sunspots can be large enough to actually cause the sun's light to dim by the same kind of amounts that we are looking for with these transits. But if it is still there, and it's there a third time, then we have confirmed that it's there, and we use another. That's another method we have to use for that. So we see the transit, and then we confirm it with another method. And what is that other method? Well, there's several. We use something called radial velocity, where we actually measure the subtle movement of the star toward us and away from us, if it's moving in that way at all, any direction toward us or away from us. And that's the actual result of the planet tugging a little bit on the star and tugging it toward us a little bit, in which case the light from the star gets shifted toward the blue as it comes toward us and shifted toward the red as it goes away from us. That's called blue shift, red shift, and it's the Doppler shift, basically, for light. You're familiar with it for sound, cars coming up, they go, that pitch change. Well, with sound, the pitch changes. With light, then we have the color changing, right? Toward the blue when it comes toward us and toward the red when it goes away. And that's a secondary method used to confirm transits, to confirm what we see with a transit. Then there's astrometry, which is something I actually did when I worked in a big observatory. We were using a kind of an astrometry program where you're doing a parallax study, studying nearby stars, hundreds and hundreds of them. And astrometry very accurately measures the position of the star in the sky relative to the other stars. And from there, you can deduce all kinds of things. You can actually see it moving and wobbling, and that wobble can be the gravitational influence of a planet, causing it to be pulled a little bit as the planet goes around it. But I got to say, astrometry has the most highest number of false positives. Okay. Another method, which is actually pretty good, is the gravitational microlens. So if you have a very, very distant star, and we're looking at a star in the foreground, okay, and that star in the foreground has a planet going around it. As the planet goes around, if that distant star's light is passing close to that planet, then the star's light in a very, very far distance will get warped a little bit by the gravity of the planet. Not a lot. That's why it's a microlens, okay? And so that's another way. Another way that we can see planets around other stars is through direct imaging, and that's usually with the infrared. Usually in the infrared, looking for what we call infrared excess. Okay, we discovered things called circumstellar disks, disks of material around the star. We discovered them that way using infrared and so forth. So those methodologies that we just mentioned, radial velocity, astrometry, gravitational microlens, and direct imaging, those are pretty much the primaries besides transiting. And TESS, the Transiting Exoplanet Survey Satellite, has already found several planets so far, and it's expected to find 20,000 plus in its 2-year lifetime. And it was just launched in April of 2019. So let me tell you, exoplanet science is not just getting a real good kick in the pants. It's getting elevated to a whole new level. TESS looks at 90 plus degrees of sky at a time to look for planets that are passing in front of their stars. Okay. The James Webb will be able to examine the atmospheres of these planets. So we're actually putting a 1-2 punch. We have a 1 up there now. We're going to put the 2 punch up, hopefully next year in this 1-2 punch. And speaking of 1-2 punch, if I don't take a break, then Bill, our producer, is going to really howl at me and really punch me out. So I think what we'll do now is just take a little break, and we'll be right back on Sky 2 Radio right after this. Hello and welcome back to Sky Tour Radio. I'm Mark Antonio here with Daryl Mason and Amanda Curran. Tonight we've already talked about the exoplanets and the transiting exoplanet survey satellite and its findings so far. TESS is amazing, and it was launched back in April, and it's going to find over 20,000 planets they suspect, and this is because this is what they think the universe has populating it. So it's actually quite a promising hunt that's coming up. However, all good things come to an end, don't they? And tonight on Sky 2 Radio, we're going to talk about the end of all things. We're going to talk about the end lives of the stars. We're going to talk about the end of the universe. I should have had an echo there. End of the universe, verse. We don't have to worry about that for, at least 4 to 5 months. I'm just kidding. We'd have to worry about that for many, many billions of years. But still, there are some really interesting theories about the end of the universe. And that takes us down the path of something called cosmology, which doesn't care about the little bumps in the road like star evolution and galaxy populations and things like that. It cares more about the big picture. And the big picture is something that is what we're going to be talking about tonight in a little bit. But first, I want to talk about the end lives of the stars. This is kind of a interesting thing to me, because every time we open up the observatory here and open the dome at SkyTour Livestream, 9 times out of 10 we will go visit something that is an area either where a star is being born or a star's died, and we just sort of gloss over it, and we don't really go into what happened there. But we have to understand that everywhere we look in the universe, it's trying to kill us. And we're trying our best. There's nothing we can really do about it yet. But we're trying to survive on a planet that's trying to kill us, in a universe that's trying to kill us. I've said before that our planet Earth is not the most habitable world in the galaxy, or in the universe for that matter. We have these very active tectonic plates. Earthquakes kill people, so we're not really the safest we could be. Ultraviolet light kills people too, by the way. It gives them skin cancer. Again, we're not in the safest place, but it's all we have at the moment. So to us, it's the best thing since sliced bread. But we haven't experienced too many loaves of bread. So when we talk about the end lives of stars, we're going to talk about the end lives of stars like our sun, and then larger stars, because that's where it really gets interesting. Not that it isn't all interesting, but normal stars like our sun, they undergo something called stellar fusion. And people know that's, in general, they know that it's basically hydrogen gas, which is mostly what the star is made of, being converted into helium. But one of the things that they may not know is that only happens in the core of the star. It's not happening all the way through the star. So you'll say, well, why is the sun so bright if it's only the core that's doing all this fusion? Well, that's because the star is outputting so much energy that the rest of the star is forced into a condition of matter that's known as plasma. The rest of the star is very, very hot material. Normal atoms can't exist in this envelope in the star, and certainly can't exist in the core of the star. The electrons are ripped out of them, and they're just very energetic protons and electrons running around, and neutrons if they have neutrons. So normal stars will be fusing atoms together, pressing them together very, very hard, okay? And this happens at temperatures that are, well, for, say, converting hydrogen into helium. To get that, you have to have a minimum temperature of 13 million Kelvin. Now, what's that? It's 24 million degrees Fahrenheit is what it is. 24 million degrees. It almost sounds like an impossible temperature, but it's not, because you can have temperatures that are in the billions of degrees. Normal fusion, which is like the regular life that it leads, it's doing something we've talked about before. It's doing something that's that fusion process is called a proton-proton chain. In reality, it's not even a chain. It's not a chain reaction per se, but it's a connected series of events, okay? So 2 hydrogen atoms will eventually yield helium, or an isotope of helium, okay? And isotopes, if you remember, are nuclei where neutrons were added to the regular atom. So in other words, the atom is still the same element, just a different variation. It's more massive, but it's still the same. So if you add a neutron, for instance, to hydrogen, it becomes an isotope of hydrogen. It doesn't become helium, okay? For it to become helium, you have to add another proton to the core of the atom, and that's very, very different. So how this fusion happens is interesting. It starts with hydrogen, the most plentiful fuel in the universe. And so 2 hydrogens are slammed together in the core of the star, not outside the core. And they form something called deuterium. It's an isotope of hydrogen. It's a hydrogen atom that has a neutron in it, okay? And then that deuterium is slammed together with another plain old hydrogen, and it forms an isotope of helium. That's helium with an additional neutron in it, okay? And that is called helium-3. And that helium is then helium-3 is then combined with another helium-3 to make helium-4. And that gives off 2 more hydrogens, which go back into the process to do it again. So, eventually that hydrogen is going to run out. Okay, and when that hydrogen runs out, for a sun-sized star or smaller, less fuel, that is less hydrogen, will foster a contraction of the star. Now, it's hotter in the core, and if the temperature reaches 100 million K, okay, then it'll probably fuse helium into carbon because that's the temperature required to do that. And if hydrogen is brought closer to the core when the star collapses, because, and I'll explain why in a sec, as hydrogen is brought closer to the core, as the star collapses, it gets hotter and under more pressure. And remember, the entire star is made of hydrogen. And as the star collapses, that outer hydrogen is being drawn into the core a little bit. And now that could be a new fusion source as it gets hotter and under more pressure. And so now suddenly the star can have more hydrogen and fuse that into helium. And when that happens, it creates this little onion skin shell around the core, and it begins fusing into helium there, right? And now the inner core of the sun, okay, will have like this inert helium that's not going anywhere at that point. All right. Meanwhile, there's a shell around the core with this hydrogen that's making more helium. Now, that extra shell fuels an expansion of the star. All right. And that's when the sun will swell into this big, massive red giant. And depending on how big it gets, it could swallow Mercury, it could swallow Venus and the Earth. It may not swallow Earth, but it could. There's competing things that say, well, it'll only go just about to swallow Mercury, and that'll be it. That'd be great, but it's still going to spell the end for us. So fusing helium into carbon in the core, and then hydrogen into helium in a shell outside the core is what this would be doing. All right. And so that said, successive elements, will actually begin to fuse in these shells around the core. And the sun is too small, too low mass to actually create, say, higher elements than, say, helium and, as we'll see, possibly carbon and oxygen. Okay, but as the star swells into this red giant, when it runs out of that hydrogen, it starts to swell, it contracts, starts to burn more hydrogen, boom, it puffs up. When that happens, that star will then vary in size, and it'll be variable. It'll puff off the outer layers, and these layers are hydrogen gas in that outside envelope, and other elements that are dredged up from deep inside the star. And Daryl, you have a comment, I think, yes?
Yeah, Mark, what you just described with helium, is that the so-called helium flash? And if not, could you define it, please?
Well, the helium flash actually occurs when the helium in the star, in the core, actually reaches a high enough pressure and temperature to actually fuse into carbon. And if you notice, I'm kind of going down the periodic table, and there's a reason that that's happening, as we'll see. And so that helium flash is another point in the evolution of the star where the temperatures of 100 million Kelvin are reached, and that helium can flash and just begin fusing as well. And that's again, it's inert in the core for a while. That's why I said it was an inert in the core, at least for a period of time. But the point in time when it begins to fuse again, that's the point at which the helium. Meanwhile, the hydrogen could be flashing, can be actually fusing in the outer shell, the onion skin outside the core, but the helium doing nothing until it reaches that pressure and temperature. So, as the hydrogen outside, for instance, begins to run out, then the star is going to contract again, and that always leads to higher pressure and higher temperature in the core of the star. And if it gets to 100 million Kelvin, well, then the helium goes off, and then we have helium fusion, and we get higher elements. So hopefully that explains. So.
Yeah. Sorry.
Okay. No, that's fine. So the star can vary in size at this point when it's a red giant, and it depends, because what happens is, as it gets more fuel, and it depends on the mass too. Stars like our sun might be less variable than heavier stars that are still going to be white dwarfs eventually, like that die kind of peacefully, so to speak. Um, so that outer envelope of the star, as the star pulsates, and these stars do pulsate, it gets sloughed off. As the star puffs and pulsates about, and now that sloughed off outer envelope of the star will contain elements such as oxygen and hydrogen, smaller stars like the sun, and additional elements in stars larger than the sun. Okay, and the key thing is that uh, the atmospheres of the stars, those outer envelopes of the stars, they become convective, like a boiling pot of water. And you know how it is. Convection cells go all the way to the bottom of the pan, and they go all the way to the top of the water. Well, same thing in the star. These convection cells can be very deep. And in fact, there's a well-known process called the dredge up. And that's what we're talking about here. When the star becomes this red giant, it might begin to start dredging up the materials that were made deep in the star, in the core. Those could actually be dredged up and brought to the surface. And those are the products that we may see in this puffed off outer envelope of the star when it starts to pulsate and puff off this material. Now, you might say, well, wait a minute, but the star has all this material and the star's gravity is holding it all together. Yes, but you have to understand the size of the red giant. It's so big. Those outer layers with deep convection cells going all the way down near the core, those outer layers are so tenuously held by the star at that point because they're so far away that they could, with the slightest provocation and energy of, say, a new shell beginning to fuse, that new radiation pressure pushing out could easily push that material away from the star forever. And we see that. We see that. And it creates a nebula around the star, a nebula that we call a planetary nebula. And Daryl was kind enough to loan me a particular filter so we could look at a certain planetary nebula. It was beautiful. And, we actually spent a lot of time in SkyTour Livestream looking at these planetary nebulae. And they all share something in common. And Amanda knows what the answer is to this, what they share in common. And it's a color. And the reason that I know that is because she has a favorite. Now, Amanda, tell us the color that you so enjoy.
Blue?
Yeah. It's sort of a bluish green. And we're actually looking at what I mentioned before. The outer envelope, has this dredged up material in it, including oxygen and some hydrogen. And oxygen, when it's ionized by the hot stellar core that's left behind, will start to emit. And when it emits, the light it emits is sort of a bluish green. And that's actually kind of where we're going with this. So the thing that's interesting is, okay, this material that left the star is that planetary nebula that I was telling you about. Now, once the fuel runs out entirely in a star like the sun, the star will begin to shrink, and it becomes a white dwarf. Now, what is a white dwarf? Well, as a star collapses, the pressure in the core increases, and atomic particles in the nucleus are pushed very close together. There's no more fusion. It's done. But the leftover heat, that's in the white dwarf is from the previous fusion products and the heat generated from the previous fusion. And the atomic nuclei have electrons surrounding them, right? They're not in the atoms, they're surrounding them. And when the pressure causes the electrons to fill every single available location in the core and in the, they're called energy states, in the energy states, then you can't crush them any more than that with a star like the sun. And it all depends on the mass. So, for instance, imagine a 1-foot diameter bag, and it has 5 small marbles in it. Okay, little ones, size of your thumb. Well, you can squeeze that bag down, that 1-foot bag down, probably to about 3-4 inches, in size, maybe 2 inches if you can really squeeze. All right, because those 5 marbles don't take up a lot of space. But if you fill it with more marbles until the bag barely closes, fill it to capacity. Okay, of the 2 bags, which would be easier to compress? Obviously, the nearly empty bag would be easier to compress. And that full bag of marbles, when you try to crush it, it pushes back on your hands as you try to crush it, but you can't compress it any further. Well, the white dwarf is a full bag of marbles with no room for further compression. The marbles are electrons. And the resistance that the star feels against further compression, all right, is the pressure from the closely packed electrons pushing outward. So the white dwarf is a bag full to capacity of marbles, and the pressure of the electrons pushing back in the white dwarf is called electron degeneracy pressure. Okay, so white dwarfs are bags full of marbles that you can't crush any deeper and any further, because at the mass of the sun, that can't happen. All right. Now, eventually, the white dwarf will cool since it's no longer fusing anything or any elements in its core, and it's sort of a quiet death of a star, and it will be the same kind of death for our star. Now, stars whose cores are less than 1.44 solar masses, and I'll tell you why that number is important, they will become stable white dwarfs. How big are they? They're about the size of the Earth. The Earth is 8,000 miles across. Our sun's 865,000 miles across. Well, that entire star, after it sloughs off a little bit of the outer layers, will be compressed down to the size of the Earth. All right. Now, there's going to be a lot of heat in there for a couple of billion years, no doubt. Now, translating the meaning of this a bit, it really means that below 1.44 solar masses, this electron degeneracy pressure I mentioned, the full bag of marbles pushing back, it can hold off further collapse. And that's the magic number, 1.44, and it's called the Chandrasekhar limit. And it's named for Subramanian Chandrasekhar, who refined the thoughts on this process back in 1930. Now, this Chandrasekhar limit is very important because that 1.44 magic number means that below that number, a star, if that 1.44 is the solar masses, and if the star only has that much or less, in the end, the core, then it can be a stable white dwarf. Now, larger than 8 solar masses, okay, we have a spectacular end. And it's primarily because at their end state, the cores of the star are higher than that magic Chandrasekhar limit of 1.44 solar masses. So they can't be stable white dwarfs. How do those stars end? Well, if you look at the periodic table, you can get some help here. In general, and nobody wants to look at the periodic table, it's like chemistry, and they hold up their hands, make a cross. No, okay. But the fact is, everything in the periodic table is made in some process via stellar furnaces, okay? Now, for the most part, there's a couple of elements that aren't, except for the ones that we make. But let's look at the periodic table. In general, we can expect the sun to make helium from the hydrogen, okay? And perhaps some carbon and oxygen near the end, all right? Massive stars, though, have a different architecture in their insides, but follow the periodic table as well. So hydrogen will make helium. That's the first two elements in the periodic table, okay? Helium, and then comes lithium and beryllium and boron. Well, helium does fuse to lithium, beryllium, and boron, but these elements are destroyed by various processes inside the star, okay? So there's not a whole lot of that around from these stellar, what they call nucleosynthesis, the generation of further products in the periodic table by the stars. Carbon, however, is not a volatile, and that can survive. And, okay, it's next in the periodic table. Then nitrogen, oxygen are formed if the star is massive enough, and fluorine is actually special, F on the periodic table, as it's also easily destroyed by the stellar products. All right, so fluorine is a special one. It's actually, I think it's like the 24th most abundant, I think. I could be wrong. But it's actually, created in ways that make it possible that we can actually use it. We use it in our toothpaste for fluoride and so forth. But the fact of the matter is, it's nearly all destroyed. So the only fluorine and fluoride that we have, fluorine, I should say, that we have, is what we could get from the stellar processes that came here and put this material into the Earth's crust and so forth, and we could get it out. Now, the list goes on down the periodic table, all right, but it ends at iron. Iron's very stable, and to force iron to fuse requires stupidly insane amounts of energy. So, and I like that, stupidly insane, because that's actually what really explains it, So because the star would get less energy out of fusing, iron than it would have to put into fusing iron. It's a natural limit to normal stellar nucleosynthesis, and that normal limit is a very important limit. Okay, so because a star, does that, we have to say that iron is the endpoint in the periodic table for high mass stars that they make in their cores normally. Okay, this is during that normal fusion process where we have all these shells that happen in the star, and iron's number 26. And we got a heck of a lot more elements. Okay, so beyond iron, other processes occur to create these elements. We've talked about these before, but in case you want to look them up, we have the S process, that's called neutron capture as well, and we have the R process. It's S for slow, R for rapid. And these are processes that actually build additional elements in a star. So at some point, massive stars look like this. We have an inert iron core because it can't do anything beyond iron. We have a silicon fusing shell outside that. Outside that, we have an oxygen fusing shell that's making oxygen atoms. Outside that, we have neon, and beyond that, carbon and helium, and then finally a hydrogen shell outermost. Okay, so stars can be a very complex onion skin layer of fusion at many different levels and depths in the star. And these are all in the core. Now, and these large stars can have many of these shells all fusing simultaneously. You can imagine that this process can wax and wane, per shell, causing instabilities in the star. And usually these are variable stars. They'll vary in brightness and their size. They will pulsate. This is kind of their nature. The more shells you have, the more things that can go wrong, basically. So, and all stars, remember, the reason they pulsate is because all stars balance this outward radiation pressure with gravity. And it's trying to crush the star in its own mass, trying to crush it with its gravity. Now, a star reaches an equilibrium point where the outward force is, equal to the crush of gravity, and that's called hydrostatic equilibrium. Don't worry about the words. It's just it reaches equilibrium, and that will hold the diameter of the star at some value for what's being fused right then and there. All right. So when all the fusion's fuel is exhausted, the collapsing force overwhelms the star, and the collapse occurs quickly. How quickly? Well, the collapse can occur at a quarter of the speed of light, right? A quarter of the speed of light, the core of that star can collapse. And the collapse, it collapses until the core can't be crushed any further. And the intercollapsing core bounces off of the inert stuff in the center and runs smack into the other infalling stuff. I mean, it's a mess. And this disrupts the star entirely. And by disrupt, I mean blows it to smithereens, So shock waves get generated when this stuff starts bouncing off the inert core and bouncing back out into the other stuff that's falling in. And it literally brightens to billions of times the brightness of the sun in minutes. This is why we see supernovae, looking like stellar points of light in galaxies that are tens of millions of light years away, And Daryl, were you with us when we were looking at the supernova in that distant galaxy in Skytour livestream? Did you see that with us?
I did. M77.
Yes.
A couple of months ago, something like that.
Yeah, wasn't that amazing?
It was. That one supernova star was as bright as all the rest of the billions and billions of stars in the galaxy.
Yeah. Yeah. And that's what happens, folks, that this is something that supernovae do. And right now you're probably thinking, do we have any supernovae that's going to happen around us? Well, we do. And we're going to talk about those too in a little while. Yes, I'm going to make you wait. It's really, don't worry. It's not going to kill us. Well, not right away. Anyway, those outer layers that get blasted off the star by this rebounding bounce, how fast do they get blasted off? Well, the answer is that the astronomers actually created a cosmic speed trap of sorts. They saw a particular supernova, and it's 10,000 light years away, so it's in our galaxy. Our galaxy members over 100,000 light years in diameter. And they saw material flying away from the star at 8 miles per second. That's 28,800 miles per hour, or 46,300 kilometers per hour, for those keeping track. Now, there is something about what happens to these the stellar cores. Remember, when this stuff blows off, there's a remaining mass that remains behind. Now, if that mass is greater than the 1.44 solar masses, then something else happens to the star. All right. And we'll talk about that when we come back after our next break. Thank you. We'll be right back. Hey there, welcome back to Skyter Radio. Before the break, we were talking about these stars that were much more massive than our sun. And when they finally run out their fuel, they actually explode in a supernova. And that core that's left behind of that supernova, what's left, the stellar remnant, there's a star-like object in there, okay? And if it's less than 2.01, another magic number, solar masses, and it's greater than the 1.44 solar masses, which was that Chandrasekhar limit we talked about, then the star does something very different. It becomes a neutron star. And a neutron star is a star basically, made of neutrons. It's like, well, how can that possibly be? Well, we'll describe a little bit of how that happens. But really what happens is a neutron star, where a white dwarf star is the size of the Earth, a neutron star is about the size of Manhattan Island. Okay, the compression is so much more, and it's more massive on top of that. So that's impressive, Now, the way it works is as a star collapses, it results in a supernova. The core is compressed further to the point where any electrons are combined with protons to create neutrons, all right? And the core can't collapse further in stars less than 2.01 solar masses. That's the highest mass of a neutron star that we've found, okay? And the pressure of the neutrons pressing back against the gravity trying to collapse the star further is called neutron degeneracy pressure. When we were talking about white dwarfs, it was electron degeneracy pressure. Well, this is the next step. If it gets massive enough to collapse, to go beyond electron degeneracy pressure, then the star will make neutrons in its core, and then the neutrons are slammed together so hard that in the same bag of marbles analogy, where the 1 foot bag of marbles is filled to capacity, the marbles are now neutrons instead of the electrons in the white dwarf case. All right. And so then we have this incompressible bag of neutrons, and that's a neutron star. At masses higher than 2.01 solar masses, the collapse continues, and it goes slicing right past electron degeneracy pressure. It obliterates neutron degeneracy pressure and goes right into black hole territory. Now, we should do a show just on black holes at some point. They're absolutely, well, they're mind-boggling, and they'll probably leave you scratching your head more than tonight might leave you scratching your head. But we're talking about things that are right now. These are fundamental findings in astronomy right now. Pretty interesting. Now, I mentioned before about stars that are likely to go supernova nearby, and I know of two, and I want to see if Daryl or Amanda knows. Daryl or Amanda, do you know a star nearby that may go supernova?
Do you mean besides Betelgeuse or Antares?
See, that's Daryl's way of saying yes, of course. What's that, Amanda?
I knew it was Betelgeuse too.
Fantastic. See, yes, Betelgeuse is the brightest star in the constellation. Well, it's Alpha Orionis, but the brightest star isn't Betelgeuse. It's actually, I think it's Rigel, isn't it?
Yes.
Yeah. See, Rigel's brighter than Betelgeuse. Yet Betelgeuse is called Alpha Orionis, and that's kind of interesting because that makes me wonder whether Betelgeuse has dimmed over the millennia here. That we've seen it in the sky. I don't know, or it's just a naming convention, because the alpha wasn't brought into play until just relatively recently, recent decades. So, but Betelgeuse is between 430 and 640 light years away. So it's really uncertain. You'll see several. I usually run with 492 light years. Why? I had to pick a number. Okay, and so if Betelgeuse is 492 light years away, it means that the light we see from it right now in the sky, and it's up there right now, it's clear here, and the Betelgeuse is right through my porthole. My studio space here where I do the show is made up like an old battleship office. I've got real portholes for windows. I've got a hook hanging out of a hole in the ceiling. I've got, weld beads and rivets on the walls. It's like a movie set. But I figure if I have to work here, it's got to look cool, And I do a lot of Navy work, so whatever, So through my porthole, I see Orion, and I see Betelgeuse in particular. So Betelgeuse, if it's seen now, we're seeing it as it was 492, your number of light years distance here away, and it's like that's how many years in the past we're seeing it. So if the supernova occurred with Betelgeuse, say 50 years ago, we're still not going to see it until that light train that had left Betelgeuse with the supernova reaches us. It's like a long continuous train of light, and when that finally reaches us, then we'll see it. The universe is a big time machine. You can always look back in time. All you have to do is look up. And sometimes you can look back in time tens of millions of years or a few seconds, like when you look at the moon, you're looking back in time just a second. And just over a second. And when you look at the sun, you're seeing it as it was 8 minutes ago. And I used to actually do a talk called When the Sun Goes Out, what would happen to the Earth. And within 7 days, which is kind of an interesting number, all life on Earth will be gone within 7 days of the sun going out. And there's a lot of reasons why and all that, but pretty interesting stuff. And, Antares is a very interesting star. It's Alpha Scorpius, and it's like 620 light years away. And Daryl, I bet you got something you want to add to this.
Well, you were talking about, I guess light from the sun, and it's going to go out, and distance of the distance the light has traveled. Uh, I was thinking this earlier when you were talking about stellar evolution. That consider the sun is 850,000 or so miles across, and all the fusions going on down in the core,
Yeah.
and there is so much matter in there that it takes that photon that's emitted when a particle fuses. It takes it like 100,000 years to escape the sun.
Yeah,
Okay, it
that's
takes
right.
100,000 years to go 400 some odd thousand miles, and then once it breaks free at the surface, it only takes 8 minutes to go 93 million miles to reach us.
Yeah, and that's a point I didn't make, but that's a very good point. Thank you. That see what what he just said is true, and the reason it happens is because the photon is getting thwarted as it's coming out of the core. It's hitting other high energy protons, okay, and hitting other materials, and it's getting absorbed and bounced, and so the chances of it getting out of the sun straight uh, are none, actually zero. No photons ever left the sun as far as we can tell from calculations. And I actually, for when I was getting my astronomy degree, we actually had to create a model of a star. We had to actually make a functional star on the computer. So not, I don't mean just a circle with bright lights shining. I mean, using all the equations that deal with stellar nuclear fusion, we actually had to create the different core elements, the shells, and create a star that would evolve. And so that was probably one of the most incredibly enjoyable projects I ever did. That was just a big computer program that we wrote. But I'll tell you this, you learned an awful lot about how stars really work when you go through this. And that's what we learned, that a photon created in the center of the star is going to take, as Daryl said, 100,000 years to actually get out. I mean, that's like being in the most crowded room you've ever been in. And every time you're trying to get to the door, you just can't get out. You just get somebody else grabs you and pulls you away, and then you bump off somebody else and you turn the other way. And oh no, when am I going to get out of here? So there's that's what's so interesting about stellar fusion and the creation of energy in a star. And yes, 100,000 years, and he says 8 minutes to get here. That's very true, very true. Now, with stars that are red giants like Betelgeuse, we can just imagine how long it takes for a photon from the core to get out, because Betelgeuse is massive. It's not, the 860,000 miles across that the sun is. It's actually much, much bigger. Antares is even bigger. So we find that, stars like that, these photons aren't going to get out, for a long, long time either. Now, Antares is the eye of the scorpion, Alpha SCO, Alpha Scorpius, and it's going to be destined to go supernova too. Now, it's 620 light years away. Now, you may ask, do we have anything to worry about? If Betelgeuse is 492 light years away, could that eventually hurt us? Well, the only thing we'd have to worry about is high energy radiation that could damage our ozone layer. Now, if we had, say Alpha Centauri went supernova, it can't. It's not nearly massive enough. But let's say it did. That star system could damage our planet. Okay. It could damage our planet because it could actually affect our ozone. And I did misspeak earlier. Daryl corrected me just now. Antares is the heart of the scorpion, not the eye. Like I said, I'm an astronomer. I'm not a constellation guy, but that's okay. I told him to always, not be shy about doing that. Thank you, Daryl. So at that distance that we're looking at for Alpha Scorpius, okay, we don't have a problem. But if it was Alpha Centauri, then we could be in big trouble. Our ecosystems could be destroyed. We could have our ozone stripped away. That means ultraviolet light that is being thwarted by ozone would come coursing down into our atmosphere and make its way to the ground. And we know what happens when ultraviolet light gets through the atmosphere and gets to the ground. Look at Mars. Okay. Mars eventually lost its atmosphere for a number of reasons, namely the ultraviolet light would disassociate any water molecules in the atmosphere. What's disassociation? It rips it apart. So water molecules are 2 hydrogens and 1 oxygen. And that bond was ripped apart by ultraviolet light coming from the sun. Even lower in the atmosphere of Mars, it didn't matter. Even at ground level, that's photodisassociation would occur anyway. So over time, over millions of years, Mars lost a lot of the water in its atmosphere. But there's natural processes that create it. And as Amanda and I have talked about before on Sky Tour Radio, there are ways in which we can terraform that planet. But do we have a right to? That's the question. Is there life there underneath the frozen ices? The South Pole or such and such. We don't know. So who are we to say that we have a right to do that? So anyway, nearby supernovas, we only have Betelgeuse and Antares. And we don't have anything to worry about from them. So call it luck of the draw. But see, we're circulating around the galaxy. And as we go around the galaxy, we come into the proximity of other stars and will. And as we come into the proximity of other stars, well, it could be that we will eventually come near a giant star at some point that goes supernova. And maybe it could strip our atmosphere away, like the same way Mars lost its atmosphere. And that would cause some big problems for us. So we better learn how to get off this planet sooner than later. And what's that mean? Well, if we can get off of here within a couple of million years, then I think that we have half a chance, probably sooner. But it may all be for nothing because, frankly, the universe is not permanent. There's an end to the universe. Yeah, I know. It doesn't sound really encouraging, does it? And you might be thinking, why do I even listen to this guy to a radio, man? It's like doom and gloom. No, it's really not, because it's many billions of years in the future. All right. However, I think it's important to understand how the universe could end so that you can see where our science is going to go. It may be the end of the universe, but it might not be the end of humanity. Yeah, and maybe we'll get to that when I get near the end here. But let's talk about the theories of the origins of the universe first, because that sets up the end of the universe. In 1927, Georges Lemay thought of a concept called the Big Bang, based on data that they had been seeing, and that theory was actually opposed by Sir Fred Hoyle. And Fred Hoyle was a very well-known astronomer, and he came up with a theory called the steady state theory. Now, that was 1948. Okay, so these were two competing theories at the time, and no one really knew which one was the right one. And they each had their attractors and detractors. Now, the steady state theory basically said, and I'll go to the Big Bang in a minute. The steady state theory said that the universe is expanding, but the density of the universe remains the same as new stars and galaxies were being created at the same rate as the old ones. Okay, but the old ones were becoming unobservable from here because of the distance and velocity that they're leaving us behind. All right, so the steady state, couldn't define a universe that was not that was constant, actually, and not moving. Okay, the steady state had to include the fact that the universe was expanding, because that's something that was pretty obvious. But Edwin Hubble, back in the 30s, he basically figured, well, not only is the universe expanding, okay, he studied the standard candles for distance, and these are known as Cepheid variables in these distant galaxies. And we've talked about Cepheid variables and how they're used as what we call, part of the cosmological distance ladder, okay? And Cepheids with a certain, they're variables, meaning the stars vary in brightness, but they vary in a very specific way, okay, with a certain period of oscillation. That'll always be a certain intrinsic brightness associated with their period of oscillation. So no matter where we see them, we'll be able to calculate the distance to them, okay? And the study of those Cepheids showed that the universe is also expanding. And from then on, it was a matter of how much it was expanding and whether the density of the universe would mean that the universe was open or closed or something else. I mean, and we're talking about open or closed, excuse me, open or closed or even flat. No, I don't want flat earthers out there to go, what? He said flat. That's not what this was. Okay. We're talking about a geometric Euclidean geometry here. So open, closed, or flat has different connotations here. Okay. So it's not like the flat earth nonsense. And I'll explain that in a little while. But basically, if there was enough density in the universe, then maybe the universe could start to slow down and then contract, okay, and start the whole process over again. Or if there wasn't quite enough density in the universe, maybe it'll continue to expand forever. See, so now, and what that's that. Now, the open, closed, and flat have to do with the shape of the universe. Is it just a big sphere? What is the universe? And that's something else that cosmologists, they love to puzzle over these things, probably on vacation while on the beach, But I'll tell you, the further analysis of motions of these distant galaxies really found that the galaxies, again, this was Edwin Hubble, the galaxies are receding from each other, okay? Now, Amanda did a great little demo from something I had mentioned in Sky Tour Radio way back, almost a year ago, I think. And I think it shows you why all the galaxies are racing away from each other. And I'm talking about on the global scale. I'm not talking about galaxies that are in clusters of galaxies, because those are all kind of moving around each other and orbiting each other and passing through each other and doing all kinds of things together that way. But on a much bigger scale, all the galaxies and the galaxy clusters are running away from each other. Now, how could that possibly be? But I think if Amanda wants to explain, she can explain the demo that she did to show that on her channel, Danny Fan 1, DHANIFAN 1. So take it away, Amanda. Just tell folks that if you don't mind. I know I'm putting you in the spot.
No, if you take a deflated balloon and draw a whole bunch of dots on it and measure them, they're all at a certain length from each other, a distance away from each other. But as you blow up the balloon and add air, everything expands and those dots move further and further away from each other. And I like Daryl's analogy of the raisin bread. If you put raisins in some dough and bake it, because then you have more of a three-dimensional image.
Yep. That's very good.
Yeah. And the farther apart the two raisins are, or the two dots on the balloon, the farther apart they are when they start, the more it expands, the faster those two are moving apart from each other. Yep. And if you go twice as far apart, you pick another raisin halfway down the loaf, well, they're moving twice as fast again.
Exactly. You come to Sky Tour Radio and you leave feeling you want a balloon and some bread. I think that's great, though. Those are good analogies. Daryl, mine was a two-dimensional analysis and analogy, and Daryl's was a three-dimensional analogy to show you what's going on. So, yes, and the farther an object, Edwin Hubble discovered that this is happening, and he found that these galaxies, like I said, were also racing away from each other in the ways that both Amanda and Daryl just told you. And that parameter of that racing away from each other was something that was found through looking at the light coming from the galaxies. Their light was shifted to the red end of the spectrum, toward the red, not all the way into the red, but the light was redder. Now, that's something called the Doppler effect. And we've seen this before, and like I said, with sound, okay, we hear pitch change. When something's approaching, making noise, you hear meow, okay, as it goes by, right? So it rises in pitch as it approaches, and it changes and goes lower in pitch as it races away. That's because the sound is being compressed on the way in and extended longer on the way out, and longer wavelengths are lower. And so you get the shift and the pitch shift. Now with light, we don't hear a pitch shift. We have color shift, as I mentioned earlier today. So we have a red shift for things that are going away from us and a blue shift when they're coming toward us. We don't see a blue shift in galaxies. We see red shift. Okay. And that's Edwin Hubble's legacy, is that he discovered red shifts. And the further an object was from us, the faster it was racing away from us. Okay. And so to that point in time, the Big Bang and the steady state theory were the two top theories. All right. And this information didn't detract from that possibility that either of those could be true. Now, the Big Bang, of course, is the primordial superatom exploded and expanded outward and so forth. There was a a lot going on. We'll talk about in just a few seconds here. But, we don't, at the time we didn't know in astronomy, astronomers didn't know which theory was more likely. And we learned that in 1965, Arno Penzias and Robert Wilson discovered something called the cosmic microwave background. What's that? Well, this was radiation left over from the Big Bang. Okay. And if we look at its thermal spectrum, we see that it corresponds to 2.725 Kelvin. So a very, very low number, almost absolute zero. And rounded up to 3K. It's called the 3K background radiation, it was also been erroneously called the 3-degree cosmic microwave background radiation. Kelvin is a scale. It's not degrees. It does not operate that way. So 3 degrees is a misnomer if you hear it. Now, its existence is completely consistent with the time when the universe had become transparent after an initial hydrogen plasma fog that was opaque. What's that mean? When the Big Bang exploded, there were no electrons. These things happened later on. And when the electrons formed, the universe was very, very hot still. But eventually, when electrons could combine and enter the nuclei of the atoms nuclei that were formed, they became hydrogen atoms, the most plentiful, as I said. And at that point, the universe started to become transparent. And when that happened, that is when we started to be able to, that's when that cosmic microwave background is something that we ended up being able to see. All right. And we call this a look back time. Daryl's mentioned this on either on SkyTour Radio or on SkyTour live stream. But such a plasma fog, so to speak, was only possible with a very hot explosive event. And that's the birth of the universe or the Big Bang. So recall SkyTour Radio, we talked about, at the beginning of the universe, the temperature wasn't cool enough to allow particles to form, in these atoms. So only hydrogen nuclei were around, very hot plasma. And then it was like an opaque curtain, and it wouldn't allow radiation out. So once the universe was cool enough and then hydrogen atoms formed, these electrons combined with the hydrogen nuclei, as I said, and then it was transparent to radiation. And what we see when we look out there, we're looking back like 13.2 billion years in this look back, and we actually see this cosmic microwave background, the CMB, okay, and that is a remnant of a massive explosion, and it's everywhere. Everywhere you look, we see it. So it really changed how we viewed the origin of the universe, and the Big Bang is what became the predominant theory at that point. And steady state went out the window because a steady state theory couldn't account for that background radiation. All right. And so that's what happened. All right. And I think that's very interesting because the cosmic microwave background that we see today, this cosmic microwave background is in every direction we look. This 2.7 Kelvin radiation is literally the blast cloud, so to speak, from the Big Bang. And it's all around us. Fred Hoyle, unfortunately, couldn't do much with it, and he had to basically relent. And so the steady state was out, and the Big Bang was now the primary contender as it is today. Now we had to explain how the universe was going to evolve and then end. All right. So how was that going to happen? And I think that's the most interesting part of where we're going to go on SkyTour Radio next. So for those of you that are interested in sticking around, hang out with us here, and we're going to tell you how the universe is going to end. It's really odd, but you're going to hear about things like the Big Rip, as in R.I.P., and not rest in peace, but the Big Rip, as in rip. You're going to hear about the density of the universe. You're going to hear about the Big Crunch. You're going to also hear about the Big Freeze. And what's it all going to mean? We'll tell you right after we come back from this break. I'm Mark D'Antonio on SkyTour Radio with Daryl Mason and Amanda Curran. We'll be right back. Hey, it's Mark D'Antonio with Daryl and Amanda back here on Skytour Radio. We were talking about the ultimate fate of the universe, and that should get your attention. Now, the thing was, we had talked about how the steady state theory that was put forward by Fred Hoyle in the 1940s was kind of dismembered and taken apart when we discovered the cosmic microwave background radiation. That's Penzias and Wilson's discovery, which showed that that was basically the smoking gun to the Big Bang, basically. And now we had to figure out a number of things. Okay, now that we have a good idea how the universe started, now we want to know what's going on with it. Is it dense enough to expand forever? You know, that is to say, does it have a least density such that it can expand forever? Or does it have more density and it's going to slow down and then possibly collapse on itself? And we kind of think we sort of know a little bit of this answer. And there's some instruments that have actually done some measurements and so forth. We think that the universe may very well be expanding forever. And you might say, "Phew, good, we're not going to get crunched out of the way." However, I think that's probably problematic, because if we expand forever, something else happens. Okay, and we have to describe this in terms of talking about how this end actually is going to occur. Okay, it really depends on the density of the universe, and more mass and density means that expansion, which we now know is occurring, would either be slowed down or continue unabated. As I said, it depends on that density. And there's this density value that's defined called omega, okay? And the density that is omega is higher if you include dark matter, which is so far unidentified matter. It's only called dark not because it's black, but because it's unknown. But we know it's there because we see it influencing things that we can see, okay? So that means that there's a higher density based on dark matter. That leads to a possible contraction of the universe, pushing that density over that critical threshold so the universe could collapse on itself in time. But, and it's a big but, okay, dark energy contributes too, and it adds a force counter to the collapse, which is actually an acceleration of the expansion. What's that mean? It means that we've discovered, starting in 1998 and moving forward, we discovered that as the universe is expanding, it's not just expanding outward and kind of continuing, to maybe slow down a little. It's actually accelerating outward. And it's like, wait a minute, what's that? Why should it be accelerating outward? The blast occurred so many billions of years ago. Why would it still be expanding outward? Okay. Now, density isn't really affected then by the two big parameters we can't understand fully, and that's dark matter, which is 22% of the universe that we don't know, and dark energy, which is a whopping 74%. Okay, dark energy contributes as well, because dark energy is actually, the reason why the expansion is accelerating. Okay, and when we look at dark energy, okay, you can now see why dark energy's component contributes so much to that overall density and whether the universe is going to collapse or not. And it's, from what we see now, it's actually pretty likely that the universe is going to maybe slow down a little, but it's actually going to continue to expand, and that means that the expansion may very well go on forever. All right. Now, if the density was high enough, then, as I said, the universe could slow the expansion, because all the mass inside which has mutual gravity, would slow the expansion and then all collapse toward the center again. And that would be problematic, So we think now that if the density of the universe is certain, the density of the universe has certain values that they mean different things to us as to how the universe is shaped as well, and that ultimately will determine what happens to it. So we have a problem with the geometry of the universe as well. And all of this helps us define the shape of the universe, as well as the density of the universe. Okay, and that's really the part that is perplexing. So how do we explore the shape of the universe? Well, the easiest way is to draw parallel lines. And look what happens when we draw the parallel lines. Okay, and what does that mean? Well, if we draw parallel lines, for instance, on a piece of paper, we say the piece of paper is 10 miles long, you draw parallel lines the whole length, well, you're going to have parallel lines at the end. Okay, and they're not going to change because it's a flat piece of paper. Okay, and that's the simplest form of an object that we can draw that will basically be subject to the shape of the object that they're drawn on. All right. Now, if we draw it on, say, a saddle, like a horse's saddle, and go from front to back. Okay, initially you draw parallel lines, they'll be fine, but they'll diverge as you go toward from front to back. They'll diverge. On a sphere, the opposite happens. If you draw parallel lines at the equator, moving up together toward the north, by the time you get to the top, following the geometry, they're going to converge and meet. All right. So that means that we have to look at whether it's a flat geometric universe, a saddle-shaped geometric universe, or a spherical geometric universe. And the answer may actually surprise you. It turns out that the universe is actually flat geometry, not spherical. It doesn't mean it's a big long plane, not at all. It just means that no matter which way you go, parallel lines will always remain parallel. That's what that means. Now, what will happen in this really strange universe over time? That's a pretty cool question. With the finding that the universe is expanding at this accelerating rate, this acceleration could increase to the point where the acceleration is likely due to dark energy, which is likely due to dark energy. It could overpower the gravity holding things together. Now, let me phrase that again because I want to make sure that you follow, because we're talking about one methodology, one method by which the universe can die. Okay, if dark energy is causing the acceleration of the expansion of the universe, making it expand faster and faster and faster, then there'll be a point where that acceleration will be so high that the very atoms themselves will be ripped apart. Now, we're made of atoms, so is the Earth, so is everything in the universe. And basically, this is what's called the Big Rip, RIP. Okay, this is something that could be a potential outcome. All right, based on the fact that the dark energy is causing this acceleration of expansion. See, we don't like accelerations. Accelerations in astronomy and cosmology, those are bad things. Okay, because they mean in space and in the universe, accelerations don't necessarily ever stop accelerating. There's nothing to impede that. So that's kind of a real bad end, and the Big Rip would just end up destroying everything. And that's one of the possibilities. Now, instead of expanding forever and at this accelerated rate, the universe could do something different. It could reach a point where acceleration slows, allowing the gravity within the universe to get the upper hand on that outward expansion. And this would lead the entire universe to collapse on itself. Everything would go out to a certain point and then come back in. Okay? And the universe will return to this primordial superatom from whence it came. This is called the Big Crunch. Told you we're going to talk about crunches and rips and yeah. So that's one possible way that the universe can end. Second possible way, actually. And another very final and apparently incredibly final way in which the universe can end relates to the fact that it's apparent that the universe is expanding and will continue to do so forever. So now that we know that, we know we're not going to see a big crunch, right? Because it may slow a little as it expands and accelerates, but that acceleration is going to be slowing down here. But it will never stop expanding. And there's a law of thermodynamics that states that in a closed and isolated system, that's the universe now, entropy, or the amount of disorder and chaos, increases as objects move farther apart from each other. Ooh, that's what we're doing in the universe. Okay. All right. So what? So what's that mean? So as the universe expands, objects are moving farther from each other. They're going from closer and more orderly to more distant and less orderly, more chaos. So, and these are by the way, these are kind of intellectual thought processes too that cosmologists have. Um, and so as that happens, the universe will reach a point where the entropy, okay, or this disorder and chaos, is high enough that all the heat in the universe will be balancing out. It can't get any higher. In other words, it won't be able to get the entropy won't be able to get any higher. And now, the thermal energy, the heat in the universe, is going to evenly distribute because that's what happens in entropy systems. Okay, and if that doesn't mean we're going to be burned alive. It means that all the heat is going to be distributed evenly, and that is actually through the size of the universe. That distribution will mean that we are going to be very cold. So it's kind of interesting that particular this particular scenario is called heat death, and it's also called the big freeze, and they both kind of mean the same thing, which is okay. Freezing is heat. Oh, again, I told you, astronomers and cosmologists. Oh man, we have very, very confusing concepts.
Mark, can I interrupt for a sec?
You may.
Is it off topic to talk about entropy described as information or loss of information?
No, actually, I think that probably relates. I think you might be going down a path that I was going to get into, but go ahead. I want to hear it.
Oh, well, no. I defer to you. I want
to hear what you have to say. You already started talking.
Well, okay, this is a layman's understanding, and I really don't understand it at all. Okay, I mean, this is getting into the hinterlands of astrophysics and stuff.
Daryl,
I know.
Daryl, let me just say, okay.
Yeah.
Let me just say, okay. You're calling it a layman's understanding, but let's be honest. You're with SkyTour Radio because you know a lot about this stuff, and you're being very humble. And I just want you to know that I recognize that, and everybody out there recognize that. Okay, you're an amazing guy. And I am very grateful that you joined us on Skype.
Well, thank you, but I am at my limit here. Okay, like Dirty Harry said, man's got to know his limitations, and describing what's the word? No, not entropy, but the act of entropy, entropication.
Oh yeah.
As information and not as heat, I mean, that is over my head. I've heard the term many times. I think Hawking or somebody talked about it, but that is plain and simple over my head. And I'm freely admitting that right here.
That's okay. I mean, here's the thing, okay? I am an astronomer and not a cosmologist for a reason. Okay, it's because I like to get my hands dirty in astronomy. I like to be able to see things and touch the things in a sense, either through mathematics or through instrumentation that I can work with. You're the same way, which is why we get along so well, I think, because of that, you know. And Amanda is hungry for knowledge and so forth, and so you and I both feed her knowledge, and she's grown immeasurably in this last year of SkyTour Radio, you know.
She has, yes.
Has indeed. Yep. And we're hoping that she'll make it to Pine Bush, by the way. Which is in May. She really deserves to come, and she needs to hang out with all of us there to, you know, show her what Pine Bush is all about, you know. And I think she agrees, but she's not talking at the moment. I think she agrees.
Working on it.
Yeah.
Working on it.
I know you are. That's cool. So, it goes like this. Okay, there's another way to look at this whole process. Okay. In the end, there won't be any more stars. In fact, no more light, actually. So it'll be a very cold death to the universe. Now, how is that possible? Well, stars are born from hydrogen, okay? But hydrogen is used up little by little, with less being returned to the interstellar medium than the stars started with. So over a great deal of time, hydrogen will be in short supply. And the universe will basically end up balancing out its temperature, and it'll die a very cold death because there won't be any more stars. The galaxies will have fewer and fewer stars in them. In fact, galaxies will probably disassemble themselves over time. once we don't have the gravity of the stars working together and working with each other and with the massive, supermassive black hole at the center of these galaxies. So over time, there's not going to be anything left. And that's what's known as the big freeze, you know. So these concepts in cosmology are very, very esoteric. They're very difficult to follow sometimes. But I do think that just by knowing the fact that the universe is expanding means that it's going to be cooling off more and more and more. Okay, that kind of gives you pause, because you know that at some point it's going to be either continuing to expand and cooling a lot more, or it's going to slow down. Now, the omega parameter I talked about before, if the universe is basically an open universe, meaning that the expansion will continue, then basically what the finding is that the universe is expanding, but it's expanding and it has a slight curve to that expansion line. So it means that the curve, meaning it's slowing down the expansion ever so slightly. And that is something that, again, theorized. We don't know. We don't know. But if you think about the distant future, let's suppose you believe in reincarnation. You come back where? Well, you come back in this universe, okay, so to speak. Maybe, maybe not, right? Maybe a parallel universe. We don't know, okay? However, if you come back in this universe and you believe in reincarnation, there will be a point in the future where you're going to come back to a universe that can't support you anymore. Or you'll come back at a point where life is no longer able to support itself because the mechanisms, the heat, the needed requirements for the life form that you may become at that time is no longer present. So what might happen? The question is, could we evolve to be beings that could live in an empty universe? Did you ever think of that, Daryl?
Oh yeah.
Yeah.
Ultimately the problem I have with cosmology, whichever flavor you pick, where is hope for man? Okay, where is hope for us? Hope for life, hope for spirit. Uh, well, I cut my teeth on cosmology back in the 80s, and yeah, the Big Bang and the oscillating universe were the big thing. And now it's looking like, things are not only flying away from us, but everything's accelerating away from us. And there don't seem to be any solutions that really offer any hope.
I know, right?
Life or spirit as we know it. The oscillating universe, of course, I mean, I'm a proponent of that, or I was in the day, and I don't claim to know much about the modern elements of cosmology. At least the oscillating universe, well, it offered the hope that things would begin again, okay? That, there's going to be a new start somewhere down the road. It may not be us, but maybe we'll be there. But, are we just going to fly off into space until everything is cold and black and dead? I'm sorry. The humanist in me has a problem with that and always has.
Yeah, I get that.
I don't care about dark matter. I don't care about dark energy. I don't profess to understand it. They're not even really real concepts. They're just placeholders. We don't know what dark matter is. We don't even know if it's real.
Actually, dark matter, though, we do see its effect on other things. In fact, that's when we saw the fast radio bursts, if you remember, fast radio bursts coming from distant galaxies. We found that there was a delay in the time that certain frequencies of that millisecond pulse from these fast radio bursts reached the detectors. That delay was caused by changes to the light, okay, of these fast radio bursts, because it was passing through matter we couldn't see, dark matter. And so that was actually telling us how the dark matter was laid out in between galaxies. These vast distances between galaxies are not empty. There's stuff there, and that's part of the dark matter, I see your point about the humanist in you wants to believe there's hope for mankind or humankind. But the truth is, the question is still here. In the big crunch, for instance, where the universe starts again, and you say, well, maybe it won't be us. But how about this? It may not be us in the big crunch, but in the ever expanding universe, which eventually goes dark, who's to say that we won't create our own lights using our new methods that we will have evolved to create? Because the big crunch is going to negate the possibility of survival through evolution as we know it. However, the expansion, the endless expansion of the universe, darker and darker as it gets, might be able to allow for the continuance of humanity, because perhaps we can evolve to adapt to the new conditions. See what I mean?
Yeah, well, that sounds like one of those Star Trek stories where, the highly evolved beings are little clouds of gas or energy floating around, and
Well,
you know, uh, one of them gets jealous and kills the nice one, and it turns out he didn't. It was the one with Kirk and Diana, what's her name, and Spock, the energy beings. That's. I'm sorry, I don't mean to make light of it, but
no, but see, you can, because this is billions of years of the future, and we're just talking futures here. We're not even, this isn't around the corner, so it's okay. That's why I'm laughing, because I know that these are just our musings as to how the universe might end. You see what I mean? Now,
oh yeah, well, musings. Philosophers used to muse on how many angels could dance on the head of a pin, and that's, it gets silly after a while. It just gets silly.
yeah, that's true.
And that's why I put down cosmology. I'm sorry, I don't mean to sound like a doubting Thomas here, but this is the problem I have with modern cosmology.
No, that's fine. And that's see, the problem you have with modern cosmology says something about cosmology, not about Daryl. Okay, and what it says about cosmology is that cosmology has holes that don't allow you to logically see uh, a conclusion that could allow for humanity to continue. And that's fine. Now, I used to, as a kid, I used to believe the universe was immutable. Nothing changed. It was always the same. That's what I thought. But as I grew and I realized that the universe is changing, I first learned the universe was changing by, of course, seeing the moon, different places in the sky each night. Hey, what's that? Again, when you're 6 and 7, those are the things you look at and say, what's going on there? How far away is that? You don't know distance. You might think it's on the other side of that house, in the distance. You don't know how far it is. And I'm going to embarrassingly tell you, as a kid, when I saw the moon rise one time, it was on the horizon, and I saw it behind the trees. I actually started to run down across the playground because it was coming across. It was coming up behind the trees at the playground, because I wanted to get to the other side of the playground because I thought I could get close to it. Now, I mean, that was a problem for my parents, because I think I was all of 5 or 6. Okay. And I just ran out of the house, ran right across the road, just kept right on going through the field. I got to get to that thing. I got to get to that. The moon. I got to get to moon. And of course, when I got to the trees, I saw that it was even farther away. And I went a little farther, and then I gave up and I walked home, and my parents were like going crazy, thinking that I had been kidnapped and all kinds of things. Yeah, it's another one of those crazy things I did. But you know what? We learn about how the universe changes, what happens with the universe over time. And I don't know the ultimate end to the universe. Actually, cosmologists don't even know. And like I said, I'm an astronomer. I'm not a cosmologist. I didn't want to be a cosmologist. Why? Because we don't have answers that are something that we can sink our teeth into. I can tell you the spectrum of a Wolf-Rayet star and what it's doing, and its hot stars, very massive, pre-supernova event. Okay. I can tell you about that because we have the instrumentation to look at these Wolf-Rayet stars. I sent you a photo we took of in Schedule Livestream of Thor's helmet, which is a remnant that's a nebula caused by a Wolf-Rayet star. These hot powerhouses pumping out all this radiation.
Yeah.
It's beautiful. It's beautiful blue. Again from the oxygen, atoms that are being caused to glow, and I can sink my teeth into that. but I can't sink my teeth into looking at like a whiteboard and just trying to puzzle about the death of the universe and the end of the universe. I bring it up tonight because these are the theories. These are what cosmologists do. You know, and some of this will strike a chord with some of the listeners that are going to think, man, that's pretty crazy. You know, I'd like to learn more about that. So they'll seize on maybe some of the keywords that you or I said tonight, and they'll head on out to, you know, Google is their friend in that case, and start digging to find out what they can find. And maybe they'll be able to formulate some really cool questions that they'll come back to us with. And
Yes. Well, hopefully it will improve understanding.
I hope so. Either way, I just want to mention, guys, for those of you listening, SkyTour live stream is going to commence at the conclusion of the radio show tonight. And I know that Amanda has her show on ERT Radio at 10:30, I believe. Is that correct, Amanda? It's a comedy?
That's right. Yep.
Yeah, okay, good.
Sunday Night Funnies.
Yeah, if you want to see the Sunday night, if you want to see the Sunday Night Funnies, go over to ERT Radio, and you can do there by going to Mixler.com, and you can go to YouTube and check out SkyTour live stream. Subscribe over there if you haven't already, and I'll be running the live stream tonight. And if Daryl wants to join me, he can, you know, and you can ask questions of him there too as well if he's going to join. He may or may not be available. I don't know yet because I haven't even confirmed with him that he wants to do it at all. But he's done it before. But we're asking a lot of them. We had him come out all night tonight. So
I may be back and forth at both places. Who knows?
You're welcome to join us no matter where you are. Anyway, folks, on behalf of Daryl and Amanda and I want to thank you for listening to this edition of SkyTour Radio here on March 17th, the day called St. Patrick's Day. And we hope you have an excellent night. And don't forget, keep looking up.